Okay, so hello everyone. So welcome to our this week Rogers Efficient AI seminar. And today we're very glad to have the Professor Hao Zhang from the UC San Diego and Snowflake to give us this talk, Fast Video Generation with Sliding Tile Attention. And Professor Zhang is currently assistant professor in the UC San Diego. And before that, he was a postdoctor researcher at the UC Berkeley. And he completed his PhD from the CMU. And during his PhD career, he took on leave and worked for the ML platform startup. And his research interest is actually in the intersection area of the machine learning and the systems. And we know that is right now the MLSys is a very hot research area. And he has worked a lot on several very famous ML generative AI work models and frameworks like the VIM, Chatbot Arena, Vicuna, and so on. And his research works has been recognized with the very prestigious award like the OSDI Best Paper Award and the NVIDIA Pioneer Research Award. And he also co-founded the company LMNet, and which has joined the Snowflake two years ago. And he also co-founded a nonprofit, very famous MLSys.org, which maintains many popular open models, evaluations, and systems. I believe some of you already use those products before. So now let's welcome Professor Zhang to give us this talk and about the efficient video generation. We know that it's also kind of very trending area right now. Okay, so how?
Cool. Yeah, Bob, thank you. Thank you for the great introduction. And it's a great pleasure to give a talk at the Rutgers Efficient AI Seminar. Yeah, let's get started. And today, I'm going to talk about our recent work, Fast Video. And today I'm going to talk about one work that is derived from this project. The title is Fast Video Generation with Sliding Tile Attention. Okay, let's get started. Yeah. So, like Professor Boyuan already mentioned, video diffusion models are seriously taking off right now. I believe many of you have already tried to use that, right? Offered, for example, by OpenAI or by Google. And if you look at the leaderboard on the left, you all see names like Google's Whale 2, OpenAI's Sora, and Clean from Kuaishou leading the pack. And I think recently, just in the past 1 to 2 months, we see a lot of new models, and these models are generating insanely realistic videos just from text or images, and it will generate videos. And on the right, you can see this kind of buzzword they are generating online. We are talking about very complex scenes, cinematic camera motions, and multi-character interactions, very complex and rich videos. But these are all fully AI generated. So what is powering all of this? So it is essentially the diffusion transformer, which is the backbone behind this new wave of generative video. So since not all audiences have a background of video generation, so I will first briefly introduce how diffusion transformer, or in short, DIT, works to generate video. So the diffusion process takes place inside this diffusion transformer, which I show on this slide. And this is the core of video generation model. And as you can see from this slide, in this diffusion transformer, so basically there's the input noise. Okay, the input noise here, it goes through this model, and it undergoes iterative denoising. And this denoising process is conditional on a time step t here. And normally takes around, for example, 20, 50, or even 100 steps repeatedly computing until you produce a video. This is the very standard like a diffusion process, right? And to get the generation with textual information, this attention here we have DIT blocks, and essentially this DIT blocks is composed of many like transformers, right? Everyone uses transformers today, and but to get this generation with textual information, this attention inside of this DIT blocks is also applied between both video tokens and the text tokens. Okay, and these text tokens were produced by an external, say, language model. No, the video tokens are flattened from a 3D to 1D sequence to make the transformer work, because the original input of the video is a 3D cube, and but the transformer architecture it only works on 1D sequence. So what we do is we put this video into this so-called encoder. For example, it could be a variation autoencoder, and we basically encode the video, and then we flatten it into a long sequence. Okay. And for language, I don't think how to explain it. It's pretty straightforward. It's basically a language model. And finally, decoder decodes final video frames from the latent representation, and it produce high resolution generated video. Okay, this basically give you an overview of how this DIT for video generation works. So we cannot directly run diffusion on full videos, like I said, because video data is highly redundant, very big, and very high dimensional. We cannot directly feed pixels into this DIT. So people have been trying a lot of tricks to make this practical. So one important idea to make this work is to introduce the VAE encoder and decoder, like I already briefly explained. And the function of this VAE encoder and decoder is to shrink down the input and make the sequence much shorter than the for the transformer. You can imagine like if without this encoder and decoder, how should we handle the video on transformers? So we have to flatten the original video at the pixel level, right, into an extremely long sequence. For example, even several million or even billion tokens, and then we feed this sequence into this transformer DIT block. And this is apparently not practical. That's why people introduce this encoder. We first reduce the dimension from the pixel space, and then we flatten it. Okay, so like I said, the role of this VAE is to reduce the sequence length of the flattened video tokens. Hence, it kinds of reduces the sequence length redundancy, right? Because we don't have to work directly on pixel space. Okay. Another idea is to cut down the number of diffusion steps. For example, we can catch features from earlier steps, or we can use a so-called distillation step to distill the original diffusion model into another model that requires less distillation steps in order to speed up sampling. And this basically exploits the time step redundancy in the diffusion steps. Okay, so to summarize this part, people have been exploring two kinds of redundancies in a small beam process. One is in the pixel space, we exploit the sequence length redundancy, and in the diffusion time space, we try to exploit the redundancy across diffusion steps. Okay. And now, in this talk, we are going to discover and study something less explored in DIT, especially for diffusion transformers, and that is basically attention redundancy, okay, which is inside of this DIT blocks. So let's look at a real example, Hunyuan video. So Hunyuan video is a very famous and state-of-the-art video DIT in open source. Okay, so this model basically generates a 5-second video at a 720p using a 13 billion DIT model. And I basically put its dimension here. Okay, it has 5 seconds, and this is the dimension of 720p video. And even after applying a VAE, the latent shape is still 30 by 48 by 80. Okay, and if we basically unroll this, it equals to a sequence length of 115K. Okay, and now let me talk about the crazy part. Okay, so generating a 5-second clip takes 16 minutes on a single H100. Okay, that's not just slow, right? It is real bottleneck for practical use, and we are already using the latest best GPU H100. Okay, so what is going on? So if you look at the flops breakdown on the right, attention basically dominates the computation. So at a short sequence length, I think it's fine. Like attention, FFN and QKV, like the distribution looks healthy. But if we increase the sequence all the way to 115K, okay, over 80% of the total time is spent just doing attention. And this is even after the VAE compression, okay? And this is even for, this is only for 5-second video, okay? And the root cause here is a 3D full attention in the diffusion transformer. So basically every token is attending to every other token across the entire video. And that's why we need to look at the attention redundancy. So we have already seen people reduce the sequence redundancy by using VAE and reduce time snare redundancy using fewer sampling steps or distillation. And now let's try to explore what is the redundancy looking like in attention. Like I said, attention is still untouched, and now it is the biggest bottleneck. So we ask the question, is there a way to make attention using less flops while still being efficient on hardware? Okay, then let's start talking about our technique. And we want to start by revealing a very interesting phenomenon in video DITs. So basically, we visualize the attention score from a Hunyuan video and found something pretty interesting. There's a very strong locality pattern. Okay, so on this slide, you can see we basically visualize the 4 frames at different temp, basically different timestamp. Okay, from 0 to from 20 to from 40 to from 60. And in these 4 pictures, kind of like a blur pictures, the green dot here, you can see if you pay attention, right? Like between green and yellow. So basically, this green dot marks the query token in attention, and the color region here, okay, slightly like a red and pink and purple, okay. The color region show where this query token is attending, and as you can see, even though the model technically used full attention, right, it was trained using 3D full attention, but if we plot this attention regions, it's mostly focused on nearby tokens, okay, and we can see that is that basically both in space and time. So in space, what I try to say is you can say if you look at this green token, it basically attends to a nearby region, right? In this pixel in every frame, and in time, as you can see, if you look across all 4 frames, you will see the query token and its nearby regions do not actually shift too much. Like if you compare frame 0 and frame 20, it's almost the same region, right? But if you compare frame 0 and frame 60, yes, it's substantially different, but this is very further away, right, on time. Okay, so instead of attending to the entire sequence, the model actually learns to pay attention locally. And in fact, we found that just 15.5% of the full attention space captures more than 70% of the actual attention weights. And that's a lot of redundant computation, right? And a clear sign that the full attention is not necessary at all. Okay, this phenomenon generalized across different open source DITs, like other models you probably have ever heard, like a cog video, mochi, and a step video. And this gives us a strong motivation to explore sparse or unstructured or structured attention and design architectures that match how the model actually behave. Okay, I hope this makes sense to you, this phenomenon. Okay, and we wanted to go beyond just visualization and measure this locality pattern more systematically. So we also computed the attention report, which we define as the percentage of attention mass that falls inside a local window. Okay, so the heat map on the left shows the average report for each attention head across layers. Okay, let me parse this figure for you a little bit. So basically, in the x-axis, you see the heads. So that's the heads in the like a attention, and in the y-axis, you see the index of layers, right? Therefore, basically each region, each small like a rectangle area here, corresponds to a head layer index combination. Okay, so basically, the darker the red, the more local the attention. Okay, because it calculates the attention record, which is the percentage of attention mass that falls inside the local window. Okay, and so if you look at this figure on the left, right? So what we see is that most heads across different layers basically exhibit strong locality, because if you look at that, basically the first impression is a lot of like darker reds, right? Though there is some variations. For example, there are some like slightly less red, less darker regions. So some heads are more global, but many are focused almost entirely on local neighborhoods. Okay, and on the right, we show the standard deviation across different input prompts. And as you can see, the value are pretty low. Okay, this means that this locality pattern is consistent across different video inputs. Okay, there's a very small variance. So this brings us to a key question. Can we actually exploit this locality to speed up attention? And if the model already behaves in this way, there's no reason to compute full global attention, right? Okay. So a very classical local attention pattern is called a sliding window attention. I believe most of you in this area have ever used sliding window attention. It is widely used in popular language models such as BERT, Mistral, and Google Schema, right? All three models I mentioned are open source and very popular models. And we ask the question, so is sliding window also a good choice in video generation? Okay, let's try to answer this question. So what will happen if we directly apply the sliding window attention in language model on this video DITs? So let's first refresh our memory on what is sliding window attention. And this slide shows the visualization of 2D sliding window attention. Okay, so here I try to emphasize 2D because in language model, sliding window attention is pretty natural because language model has a 1D sequence. Here I try to emphasize that we are basically applying sliding window attention on 2D image. Okay, but you can imagine plotting a 3D version of this is very hard. So let's use 2D as an example. Okay, but remember in video DIT we are operating as 3D. Okay, so as long as you can understand 2D, we can actually extrapolate it into 3D, right? Which is the case for video DITs. So the idea is simple, okay? Instead of letting each query here, this upper layer, each query attend to the entire sequence. So we restrict it to a local neighborhood window here, okay? And this neighborhood window now becomes 2D window, which is the fixed spatial and temporal region around that token, query token. So for each token, we only compute attention within its nearby region. Okay, it's a lot cheaper and it aligns well with the locality pattern I just explained, right? And this is very natural. Okay, everything sounds so like reasonable, right? So sliding window attention seems like a great idea, and it matches the locality pattern and reduce compute. But the obvious question is, why isn't it widely used, especially in 2D or 3D form? So the short answer is it is very hardware inefficient. Okay, there has been prior work on this, like Nathan and Clear. And Nathan, I'm not going to dive deeper into this paper, but it's a paper published by a Georgia Tech group, and you can understand Latin as a fused CUDA kernel that implements sliding window attention. But if you look at the chart on the right, okay, things are not so promising. So basically, in the right chart, the dark green bars shows actual kernel latency. Okay, this is the actual kernel latency. Um, but and the light green bars represent the theoretical latency based on sparsity. Like I said, you can understand the sliding window attention as a sparse attention, right? And latent clear and tail latent, they are all different implementations of this sparse attention. And because it's sparse, right? And if especially when the sparsity level is high, therefore the theoretical flops is pretty low. And this lighter green bar basically represents the theoretical latency given the sparsity and given the reduced flops. So from this chart, you can see that even with 90% of sparsity, Latin is still slower or only marginally faster than flash attention 3. which computes full attention. Okay, and despite its algorithm efficiency and higher order sliding window just don't run well on today's hardware. Okay, and let's try to reveal why higher order SWA is slow. So the reason why latent or sliding window attention is slow is because they are incompatible with flash attention. And we all know that flash attention is basically the backbone today, right? For running this kind of like a long sequence attention computation. To recap a little bit, I will assume that you have a basic knowledge of flash attention, okay? And just to recap a little bit, so flash attention performs computation block by block, okay? Instead of processing tokens individually, flash attention or FA, it basically splits the input sequence QKV into small blocks, typically in the size of say 128 by 64, and then processes them efficiently on GPU. And for simplicity, we assume that like square blocks in this discussion. So on the right-hand side, you see the attention map of typical sliding window attention applied on 2D, like this. Okay, and implementing such 2D and 3D SWA with flash attention comes down to one major challenge. So how to define its attention mask? Because the original flash attention it basically computes full attention, right? And now we want to compute sparse attention, sliding window attention. So we have to mask out a few regions in the attention map. Okay. So depending on how the mask is applied, we categorize attention blocks into three types. Okay. The first type we call dense block. Okay. With all the attention scores returned. And here I use this yellow block to represent full like a dense block or full block. So by full block, I mean when you use flight attention to compute by block, and when you meet this block, you basically compute all everything in this block because it is not masked out. Okay. So the second type I call empty block. Okay. Here I basically use this green square to represent this empty block. Okay. And by empty block, I mean that when you use flight attention to compute this block, we don't have to compute it, right? Because it is a masked out region. So it can be skipped entirely, and this computation will never happen on GPU. Okay, it can be skipped. Okay. So the third type is basically mixed block, and here I basically use this blue square to represent the mixed block. Okay, and this mixed block, what I mean is we need to return some scores while masking out others. Okay, so now you understand these three steps of blocks, and so basically in the original flash attention, okay, we only have two types of blocks, that is dense block and empty block, right? But when we introduce this sparsity and when we introduce this sliding window, we start seeing mixed blocks. And since a block is the minimal computing unit, okay, FA must compute the entire block before applying the mask. And this leads to unnecessary work. So the intra-block mask depends on both the user-defined attention pattern and the block's location within the attention map. And worse, it cannot be pre-computed. And doing so would cause quadratic memory overhead. And even in a very famous library Flex attention, which is developed by the PyTorch community, a simple causal mask adds basically 15% of overhead. Okay, so to repeat, computing the mask is very costly. Okay, and in 3D SWA, masking overhead can actually exceed the cost of computing the block itself. Because you can imagine basically infer the mask, infer this kind of like a small mixed blocks in 3D actually is very complicated than in 1D, right? Because you need to basically calculate the location, calculate the offsets, calculate on the time step, like in the spatial like positions. And this is why higher order SWA is inherently GPU unfriendly, and it produces too many mixed blocks. Okay. It may not be immediately apparent why sliding window attention can produce such irregular attention map. So I basically make this video for you, and I will give you 20 seconds to watch this video. So I think after watching this video, you will understand. Okay, cool. Let's resume. Yeah. So I think after watching this video, you already get a decent idea, right? So we first need to flatten an image into a sequence, right? In order to work with attention. So that's why, like on the right of this video, you see this very huge attention map. This is the flattened sequence. Okay. And then a common way to do this is that and then we apply sliding window attention, right? And a common way is basically we do this following a zigzag pattern from left to right, from top to bottom. And by following this pattern to slide, right? To slide over this 2D image, you basically will generate a attention map like this. And if you look at this, it's basically the same with this one. Okay? Yeah. And this is the zoom in version of this one. Okay. And this so in this animation, we show 5x5 sliding window operating on a 10 by 10 image. Okay, and that's what we get here. Okay, and now you understand why we have this kind of like a weird, like masking shapes and the patterns. Okay, in the attention map. So now you understand the problem, and we need to find a way to reduce these mixed blocks. So then let's start introducing our solution, which is basically in the title, sliding tile attention. Okay. Again, I think a demo is worth 1,000 words. So I want to give you a quick animation that shows how sliding tile attention or STA works before we dive into details. I will pass for another 30 seconds for you to watch this demo, slightly different. Okay, yeah, let's resume. So I think after watching this animation, you probably observe that subtle difference, right? So let's start by defining a tile. So in this example, each tile is basically a simple 2x2 block of tokens, right? In the previous example, it is basically sliding over the token level, but now we are sliding over the tile level, and this tile is 2x2. And instead of flattening the image in a standard zigzag or raster scan order, we basically flatten it tile by tile, so that tokens within each tile basically get consecutive indices. And this animation basically shows a 6x6 sliding window moving over a 10 by 10 image. This is 6x6, right? And this image is 10 by 10, okay? Where each tile is basically 2x2. And the result is an attention map that's much less irregular than naive window attention, okay? Now you will notice that there is still a little bit of acceleration like this, right? Okay, some like a jaggedness, but that's okay, okay? As long as the serration pattern is larger than a block size in flash attention, we will be able to execute it on GPU very efficiently. Okay, so far so good. So let's put the attention maps of these different algorithms side by side, and you can see that the latent and tiled latent both suffer from mixed blocks, where a single tile includes both active and inactive elements, right? Which are essentially these blue rectangles. And these are inefficient because the hardware still processes the whole block and needs to compute the mask, which is extremely slow. But with this STA, the serrated attention pattern gets flattened just enough to eliminate the mixed blocks entirely. Okay, and if you pay attention to this map, there's no blue like box. Okay, and that makes it much more hardware friendly and allows us to get the benefits of local attention without paying the penalty in memory or speed. Okay, so basically STA finds a nice middle ground. Okay, structured enough for speed, while flexible enough to capture locality. Okay. And like I said, I'm not saying STA is not irregular. I'm just saying STA is slightly less irregular, but by basically making it a little bit just more regular compared to the previous like a sliding window attention, we can actually start enjoying hardware efficiency. Okay, that's the key. Let's break down how sliding tile attention actually works in practice. So we start with a video shape of say L by L by L, and let's say it is cubic for simplicity, and we divided it into long overlapping tile of shape T by T by T. And now flash attention basically operates on block size of B by B, right? So we need to make sure that our tile size is compatible. And specifically, we want the flight-turned tile to match the flash attention block size. And normally, we use B equals to T times 3 to balance things practically. And the second important detail in sliding tile attention is how we flight-turn the token. Instead of flight-turning row by row and then column by column, we do it tile by tile. So all tokens within a tile, like this 2 by 2 region here, are aligned consecutive indices. Okay, and this is a subtle difference because in the original or like sliding window attention, we have 1, 2, 3, 4, right? And here we have 1, 2, 3, 4, 5, 5, 6, 7, 8. Okay. And you can see in the highlighted tile, basically tokens 1, 2, 3, and 4 are grouped together. Okay. And this way of flattening keeps each tile contiguous in memory, which is super helpful for efficiency, especially when paired with flash attention. And also to keep everything aligned, the attention window size should be a multiple of the tile size. And that ensures that each attention block stays nicely structured and doesn't break across tiles. Okay. And the last piece of the puzzle is how the attention window moves. And rather than shifting one token at a time, we move the window tile by tile. Okay, we basically increase the sliding steps a little bit. That is with the strap of a T by T by T across time and space. And for each position, we focus the attention within a local window, shown in yellow here, and the central tile in that window acts as a query. This is a query. Okay. And it attends only to tokens within its surrounding window. And this structured strat keeps things aligned with memory blocks and lets us reuse optimize the flat kernels, while still capturing the local context which we want for video detective work, right? And to conclude, okay, probably STA can completely eliminate mixed blocks, and we can prove that in the paper, but I will skip that in the presentation. Okay. Cool. I think that basically covers some high-level ideas of how STA works. And now let's talk about the implementation. So we implement sliding tile attention using flex attention, which basically allows us to define customer spatial attention layouts and dispatch them efficiently. And we can further optimize STA kernel by disaggregating the interblock mask logic from the computer kernel. And this lets us specialize wraps for different roles. For example, separating out data movement from computation. And this is a very low-level stuff, like CUDA stuff. Okay. We also build on top of Thunder Kitten, which is a library developed at Stanford, and which is basically for people to efficiently write attention kernels. The reason we chose Thunder Kitten is because it supports wrap specialization. And here, the data wrap groups are responsible for asynchronously loading only the dense blocks from HBM to SRAM and skipping over empty regions. And meanwhile, the computer wrap groups just do math, do computation, and totally oblivious to the sparsity pattern. And this separation improves both memory and compute efficiency. So how does this kernel perform? And now let's take a closer look at the kernel performance. So we define kernel efficiency as the ratio of actual speed up to the theoretical speed up based on flux reduction caused by sparsity. So in other words, this kernel efficiency metric here, it tells us how much of the theoretical savings actually turn into real speed up gains. Okay, and now here's the catch. So a lot of sparsity attention methods like clear and Latin, if you pay attention to the zeros, okay, they reduce flops, like I said right at the beginning, but they don't actually translate into meaningful speed up. And their kernel efficiency is under 10%. Okay. And even though their sparsity is close to 90%. But STA is different. And thanks to this slightly more regular attention pattern, STA gets way more of the theoretical gain in practice. And in our best configuration, STA reaches a 98% kernel efficiency and over 10x real speed up compared to flash attention 3 with which basically operates at full attention. Okay, here. So this proves STA is not just sparse, it's also hardware efficient. So how do we actually apply STA in video DIT? And we basically explored two settings. So first, a training first setting where we simply replace the full attention with STA and it works at inference. So no fine tuning, no retraining. It's basically drop-in replacement. Okay, the second type is basically a post-training setup where we do a little bit of fine tuning to adapt the model to the new attention pattern, which is sparse. And this can potentially recover or improve quality. And this also can allow us to use a more radical sparsity level. Let's look at what happens in both cases. So in a training free setting, we apply STA directly to a pre-trained video DIT model without any training. We run this on a typical latent video shape of, like I said, 30 by 48 by 80, and explored a few different window sizes, including both symmetric and asymmetric configurations. So here, window size is basically how much a window you attend to, right? And this is the hyperparameter you can tune. And depending how, and to choose which pattern to apply, and which window size to apply to at each head and layer, we need a simple greedy mask search, which is an algorithm shown on the right of the slide, which I don't want to probably go into details. But the idea is, if you remember at the beginning of this talk, I showed that the different heads at different layers, they have a slightly different attention patterns, right? That's why we need to choose different window patterns for them. Okay. And without training, we get an average sparsity of 58%. And that already gives us a 1.8 speed up. And if we combine this with T-catch, which is basically a method that exploits the redundancy across different different steps, we can push it further to around 3x. And this is without modifying the model width, basically plug in and play. And let's take a closer look at how we determine the best STA window size. So basically, we use a very simple mask search algorithm. It works by using just a calibration set of prompts to evaluate a candidate attention mask. And for each combination of inference step, layer, and head, we basically search for the window size that best approximate the full attention. Okay. So, so how does this training free setting works? I think instead of directly showing you the benchmarking numbers, I will invite you to watch a video. Oh, that's a cool video, and as you can see, by side on the side by side in comparison, you can already see that these two videos are very close, right? But the right one is like 3 times faster. Okay. So of course, we also try to compare existing academic benchmarks. But the high level takeaway is basically with decent speed up, the benchmark results compared to the original method and compared to other competitive methods, we are very, very close on the metric numbers. Okay. And now if we allow for a little bit of training, we can push STA even further. So we do this by distilling from a teacher model that's used for attention. the goal is to train a student model with STA that mimics the teacher without STA as closely as possible. And it's a very standard diffusion model distillation recipe. Okay, we have a loss which basically combines three parts: attention loss, which basically makes sure the attention output is close, and the final layer loss, which makes sure the latent is close, and finally a data loss, which ensures that the final generated video still matches the ground truth. So overall, minimize this combined loss: attention plus final layer loss plus data loss. Okay. The reason we do distillation is because this distillation setup allows STA to return performance close to or even better than the full attention. But we can turn up the sparsity level, okay, all the way up to say 90% of sparsity. Okay. But this is not doable in training free, right? Because if in training free you turn the sparsity level all the way to 90%, then the video will basically lose some fidelity. Okay. And as you can see, with training and with STA, we can turn the sparsity level all the way to 91%, and we get a very, very decent speed up, 3.5x. And this is without that T-catch. And if we combine with T-catch, these two methods are basically orthogonal, and you can get another 2x, okay, which will translate into 7x. Okay, I think that pretty much wrap up my talk today. To close this out, I want to quickly highlight the system we are building. It is called Fast Video. Our goal is pretty simple. We want to build a simple and efficient training and inference engine for video generation models. And we are optimizing everything from attention kernel to the memory layout to make video diffusion not just powerful, but also practical, both for research and for real-world deployment. And if you are interested in fast video or you want to collaborate in open source, or just want to try things out, feel free to check out our repo. And we also have a Slack channel that we can take some questions. Yeah. Okay.
Thank you, Hao. Thank you so much for this very wonderful talk. And the performance is really very, very impressive. And
Thank you, Bob. Yeah.
And so now, so any questions from our audience? You can either unmute yourself or input your questions in the chat box. I think maybe I can first to ask some questions. Yeah.
Mm-hmm.
Actually, I have several questions to ask. And
Please.
yeah. And the first one, so if my understanding was correct, so the key idea, so is that so actually so you kind of the leverage the kind of the locality of the
Mm-hmm.
of the I cannot say the computation, the locality of the
On the model. Yeah.
model,
Yeah.
and then to
Yeah.
use kind of tiring, right?
Yes.
Make
Yes.
actually so make the sparsity kind of more structured and more regular, and then kind of more hardware
Yes.
handling, right?
Yes.
And I think the
Yes.
interesting stuff is that is because for this kind of the SWA, because it's also is kind of a sliding window based, right?
Mm-hmm.
And so
Mm-hmm.
actually that reminds me of the kind of the old days that when we tackle those the efficiency issue of the convolution networks, because the
Mm-hmm.
convolution and the sliding window based, right?
Mm-hmm.
So I was
Mm-hmm.
wondering, is there any kind of the hidden connection there, or whether there's some kind of the rich research outcome when we optimize those the convnet can be also be further kind of deployed here for the future work. So
Yeah, if you look at the GIF I presented or the animation, it looks very similar to convolution because it is slide in a way that 2D image. But here the internal mechanisms are different because we are doing attention, but in convolution we are not doing attention. Yeah, I think like I said, I definitely believe there's a conceptual connection that we should operate for image and for video. We should operate in a convolutional way. But we are upgrading the convolutional computation all the way to attention, which is much more powerful. That's why today people use transformers. Yeah, yeah, yeah,
okay.
yeah.
Yeah, I see. And So in your experiment result shows that so actually there's kind of the non-performance degradation or kind of just minor performance degradations, right? As compared to
Hmm.
like the original implementation, right?
Hmm. Hmm. So
So
basically, yeah. So because you are migrating from full attention to sparse attention, right? And I think it's quite acceptable that you have some um quality degradation, like I said. But the good thing about this is that you are applying this on generating videos. And if you are doing this in language, I think you will observe that degradation very, very obviously.
yeah,
Because
that's
language model are
actually
tokens. Yeah,
right.
yeah,
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 yeah.
yeah. But if you do video to images, I feel it's much like friendly to sparse attention because it's very hard to spot that difference. Yeah. But like I said, there indeed are differences. Yeah, yeah,
Mm.
yeah, yeah.
No, so that means that actually, so in the vision domains, actually, it's kind of more tolerant.
Yeah, I
So,
would say so. Yeah, yeah, yeah.
so then a follow-up question is that so because we know that in the language domains, like for those efficient attention, like the sparse attention is kind of main category, and another is the linear attention. You must also know.
Hmm.
So I was
Hmm.
wondering, so how do you think about the possibility like that we also like apply the idea of the linear attention to the like the faster video generation, so on.
I haven't seen linear attention applied to video generation, but I know it's a quite active area of research of bringing linear attention into image diffusion. And
Mm,
I think there are a few works from Professor Song Han's group, right, from NVIDIA,
mhm.
which applies linear attention on image diffusion and have very impressive results. And I think that's a very effective direction. Yeah, yeah, yeah.
Do you think that it's had kind of potential that also to apply for the video generation as well?
We haven't tried because one reason is because implementing this kind of attention kernel is definitely not an easy job, especially in 3D space. Like you can imagine, like the kernel becomes more difficult to implement every time when you increase one dimension. Okay, language is most easy, and then image is slightly difficult, and video the most difficult. For now, for linear attention, I feel there are not many like good libraries for you to write very efficient CUDA kernels. And I think there's a system gap. That's why we choose to do sparse and in some sense, if you are able to do a very good sparse attention kernel in three, still in like in squared using square attention, I think the efficiency is pretty close. Yeah, yeah, yeah,
Okay.
yeah,
Yeah.
yeah, yeah.
Thank you so much. So,
Mhm.
uh, any questions from the audience? If you have any questions, just unmute yourself. Yep, maybe then actually maybe then I can ask some additional questions.
Mhm.
Actually,
Yeah, please.
so, uh, so actually, your motivation of this work is that to accelerate the video generation, right?
Yes,
So,
yes.
so I was wondering, so based on your observation or the interaction with the user, so typically, what is kind of the requirement from the users? So how fast the video generation that they require? So like it's the second level or the minute level or
I think there are two groups of users. One is those like in industry, because this is a very hot area. I think a lot of startups they are looking at the video generation. And for industry people, I think that they are interested in mostly in training, and they want to train a very highly efficient video generating model, and they are aware that the video generation is slow, and they are very open to do whatever kind of like attention reduction to make it fast in both training and inference. The second group of user is basically those people who use open source video generating models like Funyuan Video I mentioned. And for those people, I think uh, they have two use cases. One is inference, of course. They want to perform inference on, say, a single GPU because they only have one GPU. And for those kind of people, I think they would look for quantized attention kernels. They want to reduce the model size so that you can fit the model in a single GPU. And they want to, of course, they want to infer as fast as possible. And their second use case is basically they want to do LoRa fine-tuning, and they want to fine-tune the model using their curated set of images, for example, some anime, to have fun. And in that use case, I think if we were able to provide a sliding window attention that is much faster to compute, it would also be helpful. Yeah, yeah.
Yeah, you just mentioned that some users actually they consider, especially those that mm, users that have kind of constrained resource, they in addition like to use the sparse attention, they also consider like the quantized.
Yeah. They basically want everything to combine, like sparse attention, quantized attention, offloading. So basically, help. They are asking help to run the thing on single GPU, like whatever method it takes. Yeah,
Because
yeah,
their resource is
yeah,
pretty kind of constrained.
yeah, yeah, yeah.
So do you think that in addition to those like we use the sparse method and those are the compact models, do you think is there any kind of dimensions we can explore to further push the limit of the faster video generation?
Yeah, I think yesterday, right? Before this talk, yesterday, I think there's a Chinese startup
Yeah,
which
yeah.
released a new model called Magic Attention and Magic AI, and the company is called
Yeah,
Sand AI, and the author is basically the Swing Transformer author, right? Swing Transformer is a very famous paper in CVPR. I think that model is impressive. It basically exploit a different architecture, which is I wouldn't say different. It's basically autoregressive diffusion, that combining diffusion with autoregressive. So one key problem of diffusion is that um, you have to diffuse the entire sequence, right? And at computation, it's very different from language model. In language model, when you type a prompt, the tokens are generated autoregressively. So that will translate into a better user experience because you can stream the generated tokens to user while you are generating the next one, right? But in diffusion, that cannot be done. When you use diffusion services, what you see is basically a blurred image. It becomes more and more clear, right? But I think that model released yesterday, it was autoregressive diffusion. So you don't diffuse a segment and stream to users and then diffuse the next segment. And this too can be asynchronous. And that's an interesting part. I think, and also people like autoregressive because on one hand, autoregressive generation is faster, right, than diffusion. On the second hand, on the other hand, there are strong debate in the community that autoregressive can learn reasoning, but diffusion cannot, right? And eventually, I think people want to build word models instead of just video generators. That's why they prefer, like some people, or maybe many people, they are exploring autoregressive video generation. Yeah, yeah,
So,
okay,
uh,
yeah.
how about the opinion from the perspective of the MLCs?
I would do both, right? Because I'm kind I'm kind of like a system, half system, half machine learning, and whichever is effective, I will do. But in terms of my opinion on models, I would say at this moment, diffusion models generate a higher fidelity videos compared to autoregressive models, and many existing autoregressive video generating models, they are distilled from diffusion models, which means that you still need to train a diffusion and then you distill it into a AR model. But I'm not sure if yesterday's release changed that story. I haven't taken a deeper look at that paper, but we'll see. Yeah, yeah, yeah. Okay.
Thank you so much.
Mhm.
So, any question for audience? I just saw some sound from the audience. Okay, so if no more questions, so let's thank our speaker again. So Hao, thank you so much. So this is a very wonderful talk. We really,
Thank you, Paul. Yeah.
yeah. So this is very timely and very emerging work. So thank you so much.
Thank you. Thank you. Yeah, it's a pleasure to come here to give a talk. Yeah. Thank you. Okay.
Okay, thank you everyone. So
All right. Yeah.
thank you everyone for your attendance. And so our next Efficient SM talk will be next week, and see you next week.
See you. Yeah.
Thank you. Bye.